All right, we're going to take a look at acids and bases. There are two main theories when it comes to acids and bases. We're going to look at both of those in this video, starting with the Arrhenius theory. Now, according to the Arrhenius theory, an Arrhenius acid is a molecular compound that ionizes to produce hydrogen ions, or H plus in water. So say I had an acid like HNO3, nitric acid. Right? This is a molecular compound. When it ionizes, it's going to form H plus aqueous plus NO3 minus aqueous. Right? So this particular acid has ionized to form H plus and NO3 minus. What makes this as an acid is the fact that it ionized into H plus ions. Right? And ionization is just the formation of ions from uncharged molecules. So if I were to assign a general equation for ionization, it would be HA ionizing H plus aqueous plus A minus. Right? So as you can see, it doesn't matter what the anion is. So it doesn't matter what acid it is. We've learned about several different types of acids, but what matters to us is the fact that this is an Arrhenius acid because when it ionizes, it produces H plus and an anion. All right. Similarly, an Arrhenius base is an ionic compound that dissociates to form cations and an hydroxide ion. Right. So if I were to talk about CaOH2, this is my base. And when it dissociates, right, it dissociates because it's an ionic compound, it's going to form Ca2 plus OH minus. Right, just to balance this out, I'm going to put a 2 here. Now this shows the dissociation equation for this CaOH2, and we know that it's a base because it dissociates to form OH minus. Now, it doesn't matter what the metal is. It could be a different metal, but what's important is that hydroxide is produced, right? The hydroxide ion is produced. And dissociation, we learned about it in previous modules, occurs when a water molecule is able to separate the ions, the cation and the anion, from an ionic compound, right? It's able to pull it apart. Now, this Arrhenius theory explains acids and bases, right? We saw that acids are able to ionize to form H+, bases dissociate to form OH-. That's our definition for an acid and a base, according to the Arrhenius theory. But there is a problem, and the problem is that there are substances out there that behave like a base. That means they have base-like properties. For example, NH3 has a pH of 11 to 12 and it neutralizes acids, and we know that those are properties of bases. However, if you take a look at NH3, it cannot dissociate to form OH-, right? Because there's no hydroxide in it. It doesn't contain hydroxide ions. That's where we bring in our second theory, which is our Bronsted-Lowry theory for acids and bases. So between the Bronsted-Lowry theory and the Arrhenius theory, we can explain all acids and bases, right? According to our Bronsted-Lowry theory, a Bronsted-Lowry acid is a proton donor. And you'll see protons in brackets, I've written H+. So we're talking about an H+ ion here. And anytime for the rest of the video, when I say proton, I'm referring to H+. Right? So a Bronsted-Lowry acid donates H+ ions. And what does it donate to? It donates to a base, right? That's what we call a Bronsted-Lowry base. More on that in just a bit. So if you take a look at this example that I've drawn here, this is a reaction mechanism. And you don't have to copy this down into your notes. It's just for you to visualize and see what's actually happening. So I have here an acid, which is HCl. And this acid, I've shown you the partial positive and the partial negative. This proton is being taken or given to this H2O molecule, this water here. And that is possible because there are two unshared electron pairs on this particular water, right? So this HCl donates a proton to this H2O. And what happens? What is produced there? When that happens, it produces H3O+, right? So H2O, it gained an H+, it's going to be H3O+. And if you think about HCl and it's given away that proton, it's going to be Cl-. To summarize this, this is the reaction that we have. I'm going to write this out. Oops. So I have HCl plus H2O. And this is going to form H3O plus and Cl-. Right, so aqueous, liquid, aqueous, and aqueous. Right, and this H3O plus is what we call a hydronium ion. Right, and that is produced when HCl donates the proton to H2O. So hydrochloric acid donates a proton to a water molecule, and because it donates that proton, according to our Bronsted-Lowry theory, an acid donates protons. And because HCl gave away that proton to H2O, it is considered the acid, the Bronsted-Lowry acid. And water, in this case, acts like a base because it accepted the proton, right? And that makes this the base. So we've accounted for both HCl and H2O. One is the acid, one is the base. One gives away the proton, the other accepts that proton. And just to sort of go back and explain what's happening in that reaction mechanism, the oxygen part of that water molecule has two unshared electron pairs, right? We call these lone pairs. And either one of those can attract the H+ ion from the H2O, and that's what resulted in the H3O+. Our hydronium ion is produced. Our H2O, when it gains that proton, becomes H3O+. Okay, now I'm going to write this reaction one more time so that we can explain what we call conjugate acid-base pairs. H3O plus Cl-. So we already talked about this being the acid and this being the base. Now, what we see on the product side can be classified as conjugate acids and conjugate bases, right? So if I take a look at this acid here, whatever is left over on the product side, what becomes of this acid, that is going to be my conjugate base. And I want you to be pretty systematic when it comes to identifying these, because it can be pretty confusing when you have a reaction in front of you. So think about what the acid is. What does that acid become after it loses that proton? And after it loses that proton, we have our conjugate base. And the opposite is true. When you have a base, what does that base become after it gains that proton? That is going to be my conjugate acid. Okay, and together, the acid and the conjugate base produce what we call a conjugate acid-base pair, right? And there's another conjugate acid-base pair here with the base and the conjugate acid. So what you'll be asked to do in an assessment is you'll be given a reaction, you have to identify which is the conjugate acid, which is the conjugate base, which is the acid, which is the base, right? And I would just like you to think about this in this process so that you can clearly identify which is which. The only difference between the acid and the conjugate base is a proton, right? The only difference between a base and the conjugate acid is a proton. So using that, you can identify those conjugate acid-base pairs. Now, talking about a Bronsted-Lowry base, we did mention how water was the base in that previous example, but just to sort of clearly state it, bases, according to the Bronsted-Lowry theory, are proton acceptors, right? So they accept the H+. And this can be demonstrated in the following reaction mechanism. So in this case, I have NH3, which is my ammonia, and that is gaining a proton, right? And when it gains that proton, it's going to form on the right side NH4+, and water, after it loses that H, becomes OH-. Again, you don't have to write that down. It's just for you to see what that looks like. So when I write this reaction out, I have NH3 plus H2O, and this is going to form OH minus plus NH4 plus. So in this case, so this is different from earlier, water donates a proton to the ammonia. And because water donates that proton, that is the Bronsted-Lowry acid, right? So that fits into our definition from earlier. And in this case, ammonia accepts that proton. And because it accepts that proton, it becomes the Bronsted-Lowry base. Now, if you pause the video, I want you to try and see if you can identify the conjugate base and the conjugate acid in this reaction. But once you've unpaused, we're going to take this up. So if I have NH3, which is my base, after it has gained a proton, it becomes NH4. So because this is the base, this becomes my conjugate acid. And if I have H2O as the acid, after it gives away the proton, it becomes OH minus. That becomes my conjugate base. So now I have two different conjugate acid base pairs. So just to explain what's happening in that reaction mechanism, the nitrogen of that ammonia molecule has an unshared electron pair. We saw that. And this is what forms that bond with the H plus ion, which is the proton, to produce ammonium, which is NH4 plus. Now, you might be asking yourself that in the two reactions that we saw, in the first one, water was acting as a base, and in the second one, water was acting as an acid. And that is a characteristic of water. Water is amphiprotic. And amphiprotic just means that depending on the situation, a molecule can act as a Bronsted-Lowry acid or as a Bronsted-Lowry base. So depending on the circumstance, it can be an acid or a base. Okay,